All right, chemistry, this is your video lecture for chapter 7. This is your first part. Here's the first part. We're going to break chapter 7 up into two parts. We're going to go through sections 1 and 2 today. Section 1 is going to be a little bit on the longer side, but section 2 is shorter, so it kind of makes up for it. So let's get started. For this section, I want you to be able to explain the significance of a chemical formula. Remember, I don't want you to just tell me that the chemical formula is significant. I want you to tell me what it signifies. Then determine the formula for an ionic compound formed between two given ions. Then name an ionic compound given its formula. Notice that you have to go from formula to name or from name to formula, depending on what you're given. Then, using prefixes, name a binary molecular compound from its formula. And lastly, write the formula of a binary molecular compound given its name. Notice here, you're still going from name to formula and then formula to name. The only difference I want to point out here on this list is that the second and third bullets are referring to ionic compounds, whereas the fourth and fifth bullets are referring to molecular compounds. And remember what you can know about the compound from just those simple words. Ionic compound. We're talking about a metal and a non-metal having ionized and then their electrostatic attraction attracting and forming that bond. When I say molecule, I mean something is covalently bonded, and that means at least two non-metals. There are no ions present, just non-metals together, and that's going to help you understand which naming system you should be using at any particular time. Let's talk about the significance of a chemical formula. A chemical formula indicates the relative number of atoms of each kind in a chemical compound. For a molecular compound, remember that's covalent bonding, the chemical formula reveals the number of atoms of each element contained in a single molecule of that compound. Remember, molecular compound, covalently bonded, so we should observe nonmetals bonded to nonmetals, and that's what we see in this example of octane, C8H18. The subscript after the 8 indicates that there are 8 carbon atoms in that molecule, whereas the subscript after the H indicates that there are 18 hydrogen atoms in that molecule. The chemical formula for an ionic compound represents one formula unit because it's not a molecule, right? It's not covalently bonded, it's ionically bonded, and we have this almost infinitely repeating crystal lattice, and so the formula unit is used, and the formula unit, remember, is the simplest ratio of a compound's positive ions, also known as cations, and its negative ions, also known as anions. The example I want to use here is aluminum sulfate. We have aluminum. You can definitely see that there are 2 aluminums there, but what is a sulfate? A sulfate is a polyatomic ion that has 1 sulfur surrounded by 4 oxygen atoms. Now, it is true that sulfur and oxygen are both nonmetals, and they are covalently bonded together. However, when they exist as a unit, as sulfate, they operate as a unit and have a -2 charge. So it is an ion, has a -2 charge, but there are several atoms, so it's a polyatomic ion. In order to represent that in a formula form, we write parentheses around that polyatomic ion sulfate to identify it as a unit. And then we place the subscript 3 after the unit to indicate that there are 3 sulfates. Note that there is no subscript for sulfur. When there is no subscript next to an atom, the subscript is understood to be 1. So as we read this chemical formula, we're able to get out of it the relative numbers and types of elements present, like we've already said. In this particular equation, C represents carbon, or I guess in all equations it does. H represents hydrogen, O represents oxygen. Then we have these subscripts that you can see on the carbon dioxide. The subscript 2 indicates that there are 2 oxygens for every 1 carbon, and we can see that here. We have 2 oxygens for 1 carbon. For water, we know water, H2O. We have the central oxygen and then the surrounding hydrogens. What I want to point out that is a little bit new here are the phase of the material. Okay, we have G for gas, we have L for liquid, and then we have, not in this particular example, but we have S for solid, and then AQ for aqueous. The second thing I want to point out here is the coefficient, right? The coefficient. We have a 1, a 3, a 2, and a 3. That means for every one ethanol molecule to react in this way, we need 3 oxygen molecules, and we will produce 2 carbon dioxide molecules and 3 water molecules. If we do not have these molecules available at this ratio, the reaction will not progress. Now we're going to talk about specifically monatomic ions. Remember, mono means one, obviously atom means atom, so it's a one atom ion. Because many main group elements can lose or gain electrons to form ions by themselves, so it's just one atom. Ions formed from a single atom are known as monatomic ions, as opposed to the polyatomic ions. For example, to gain a noble gas electron configuration, nitrogen gains 3 electrons to form nitrogen ions with a -3 charge. Some main group elements, more as an exception, tend to form covalent bonds instead of forming ions. For example, it's very rare to see carbon as an ion or silicon as an ion. Because they are in group 14, they have their 4 valence electrons, and they tend to act as the backbone or the central atom in several different types of molecules. They very rarely form ions, even though they can. Now let's talk about the names, right? Because these are the issues that we're going to deal with in Chapter 7, at least at the beginning of Section 1. How do we name monatomic ions? It's very, very simple. Monatomic cations, and remember, when I say cation, I mean a positively charged ion. That means a metal. So a metal from the left side of the periodic table has ionized. We simply use that element's name. For example, when potassium ionizes, we call it the potassium cation. Now you have to say cation because as an ion, potassium is different than its original atom. So we call it the potassium cation. Magnesium, when it ionizes, becomes a +2 ion. We call it the magnesium cation. For monatomic anions, remember that means a negatively charged ion, something that has gained an electron or more. The ending of the element's name is dropped, and the ending IDE is added to that root name. So fluorine becomes fluoride, and nitrogen becomes nitride. Here's a table containing several different common monatomic ions. You see that the charge that they form is still tied to the group number that they are found in, as we went over earlier in the year. And I want to drop this idea before we move on that sometimes we have to use Roman numerals in parentheses on certain types of D block elements because they can form multiple charges. But we'll talk about that when we get to the stock system. We want to focus on naming monatomic ions. So fluorine becomes fluoride, chlorine becomes chloride, iodine becomes iodide, bromine becomes bromide, right? So those are for anions, monatomic anions. Remember, for the cations, we don't have to change the name. We just have to make sure that we identify that it is, in fact, a cation. So sodium becomes a sodium cation. Calcium becomes a calcium cation. Iron becomes the iron 3 cation. And copper becomes a copper 2 cation. Now, not to spoil too much, but I have to say that number to indicate the charge of that particular type of iron, because iron can form a +2 charge or a +3 charge. And we don't know which one unless I tell you. Copper can form a +1 charge or a +2 charge, but you don't know unless I tell you. And so that's how we tell you. Let's get into binary, meaning 2, ionic compounds. Compounds composed of 2 elements, just 2, are known as binary compounds. Now, not 2 atoms, 2 elements. You can have, 6 atoms, but they're made up of just 2 different elements. In a binary ionic compound, the total numbers of positive charges and negative charges must be equal, right? They have to balance out. The algebraic sum of the charges has to be 0. The formula for a binary ionic compound can be written given the identities of the compound's ions. So as long as we have the knowledge of the ions and their names that are involved, we can make the name for this binary ionic compound. For example, magnesium bromide is going to be made up of 1 magnesium and 2 bromides. Why 2 bromides? Because magnesium has a plus charge of 2, and we have to balance that out with 2 negative charges. But this is bromine, or sorry to say bromide, and that only has a -1 charge. So how can we completely balance out the +2? by having 2 bromides. And so the chemical formula for magnesium bromide is MgBr2. A general rule to use when determining the formula for a binary ionic compound is crossing over to balance charges between those ions. For example, aluminum oxide. First off, let's write the symbols for those ions. We have aluminum 3 plus and O 2 minus. We cross over the charges by using the absolute value, right, of these 2 ions, each ion's charge as the subscript for the other ion. Now, remember, absolute value just means no matter what the sign of the original value is, it's just a positive. And so I take the -2 charge on the oxide, and I make that the subscript on aluminum. And I take the 3 plus charge on the aluminum, and I make that a subscript of 3 on the oxide. So as we finish up, we check the combined positive and negative charges to see if they are equal. 2 times 3 is 6, and 3 times -2 is -6, and so yeah, that does equal 0. So the correct formula is Al2O3. When we write the formula for an ionic compound, here is your general rule. Okay, using the exact same crossing over strategy, refer to this succinct description. The nomenclature or naming system, that's what nomenclature is, a naming system, or for binary ionic compounds involves combining the names of the compound's positive and negative ions. The name of the cation is always given first, followed by the name of the anion. So, for Al2O3, we call that aluminum oxide. For most simple ionic compounds, the ratio of the ions is not given in the compound's name because it is understood based on the relative charges of the compound's ions. When trying to generate the name of an ionic compound, especially a binary ionic compound, we have to make sure we understand before we get started, we're talking about a metal bonding with a non-metal. And so you're going to have oppositely charged ions. Now, one step further, like we talked about already, when we have an ionic bond, the algebraic sum of the charges of those 2 ions must equal 0 for a neutral molecule, and that's what we have here. So we have a silver represented by Ag bonding with the fluoride. Remember, for that ion, that monatomic ion, we take the name of the element, fluorine, and we replace the last syllable with ide, so fluoride. And for binary ionic compounds, we're done. We've made sure that the ionic charges add up to 0. Silver has a +1 charge. Fluoride has a -1 charge. Silver fluoride. Over here with calcium, calcium is a main group 2 element, so it's going to form a +2 charge, and chloride only has a -1 charge, and so we're going to have 2 of the chlorides to balance out that +2 charge on the calcium. So we need 2 chlorides for this one calcium. Calcium chloride. We also have potassium oxide. Oxygen becomes oxide when it ionizes. And we need 2 potassiums because potassium, being a main group 1 element, is only going to have a +1 charge, so we need 2 of them to balance out the oxygen. And then sodium bromide, +1 charge, -1 charge. And so we only need 1 of each. So let's try some sample problems, work through them together. So write the formulas for the binary ionic compounds formed between the following elements: zinc and iodine, and then zinc and sulfur. First, we write the symbols for the ions side by side. So we have zinc +2, iodide -1, zinc +2, sulfide -2. Let's cross over the charges to give subscripts, right? Cross them over and down, but the absolute value of them. Then we check the subscripts and divide them by their largest common factor to give the smallest possible whole number ratio of ions. So for our first example, the subscripts give equal total charges of 1 times +2, which is +2, and 2 times a -1, which is a -1. So they add up to be 0. The largest common factor of those subscripts is 1. So the smallest possible whole number ratio of ions in the compound is 1 to 2. That means the formula for this is ZnI2. Moving on to the second example, the subscripts give total equal charges of 2 times plus 2 is a plus 4, and 2 times a negative 2 is negative 4. We can reduce that because the largest common factor of the subscripts is 2. So that means that the smallest whole number ratio of ions in this compound is 1 to 1. So the formula for this compound is ZnS. Now, we're still talking about binary ionic compounds, but we're going to look at a slightly different combination. And we're going to use something called the stock system. Because some elements, like we've seen with iron already, form 2 or more cations with different charges, right? For iron, it can be plus 2 or plus 3. To distinguish the ions formed by such elements, scientists use the stock system of nomenclature. And you can use the stock system for all types of compounds, but in general, the convention is to only use the stock system for cations that have the potential to form multiple charges. You can use it for molecules just fine. That works totally fine. And actually, I'll have you do that as part of your worksheet. And so this system uses a Roman numeral to indicate an ion's charge. When using the stock system, you first must understand the situation in which you are going to use it. You're going to use the stock system for an ionically bonded compound, but the cation has the potential to form multiple charges. Now, this is essentially going to be transition metals bonding with nonmetals. However, not all transition metals can form multiple charges. For example, zinc always has the same charge, or silver always has the same charge. But for example, tin, copper, and lead, they can form different charges. And so we can't simply balance the charges easily like we can with a normal binary ionic compound because we don't know the charge of that cation. With main group elements like a calcium or a potassium or an aluminum, we know that they're going to form the same charge over and over and over again. But with these types of transition metals, we don't know which charge it's going to be. There's no way to predict it. And so what we have to do is we have to communicate to the reader what the charge is. Now, we know that the algebraic sum of these formulas have to be 0. Sorry, the charges. The algebraic sum of the charges has to be 0. Now, iodide is a main group 7, group 17 element, so it's always going to form a -1. We see that there are 4 of them, each at a -1. And so in order to balance that out, this tin must be a +4 charge. And so we communicate that by writing in Roman numerals, in parentheses, 4, right? IV. Over here with copper chloride, right? Copper 2 chloride. Here's my 2 chlorides. Chloride being a halogen, it's going to have a -1 charge. I can see that there are 2 of them. So my copper must balance that out by being a +2. And so we'll say copper 2, right, because it's a +2 charge, chloride. Now we have 2 different types of lead. I have lead bonded to oxygen, lead bonded to oxygen. Now there's only one oxygen over here, and we know that oxygen is going to form a -2 charge because it's a group 16 or a main group 6 element. It's always going to form a -2. And in order to balance out this one oxide, we only need a +2 charge on this lead. So this lead is going to be a +2 charge. So lead to oxide. But over on this next example, we have 2 oxygens bonded to this central lead. And so that means in order to balance out all of that negative charge, this lead will have to be a +4 charge. So this will be lead 4 oxide. So let's get into another sample problem. Write the formula and give the name for the compound formed by the ions chromium 3 and fluoride. So first we're going to write the symbols for the ions side by side, writing the cation first. Then cross over the charges to give the subscripts. Right? We send the 1 from the fluoride down to the subscript of the chromium, and then the 3 charge on the chromium down to be a subscript on the fluoride. The subscripts give charges of a +3 and a -3. So the largest common factor of these subscripts is 1. So the smallest whole number ratio of ions is 1 to 3. 1 to 3. So the formula is CrF3. But we know that chromium forms more than one ion. So the name of the +3 chromium ion must be followed by a Roman numeral indicating its charge. And so the compound's name, right, because we just did the formula, the name is chromium 3 fluoride. Now, many common polyatomic ions are oxyanions, which are polyatomic ions that contain oxygen. Some elements can combine with oxygen to form more than one type of oxyanion. For example, nitrogen can form nitrate or nitrite. The name of the ion with the greater number of oxygen atoms ends in ATE. The name of the ion with the smaller number of oxygen atoms ends in ITE. So we have nitrate and nitrite, and the endings in those names is based on the number of oxygens present. It doesn't mean that any ATE ion has 3 oxygens and every ITE ion has 2 oxygens. No, it's a relative thing. Whichever has more is going to be called an ATE, so in this case nitrate. Some elements can form more than 2 types of oxyanions. Chlorine can form something called hypochlorite, chlorite, chlorate, and perchlorate. In this case, the anion that has 1 fewer oxygens than the ITE anion is given the prefix of hypochlorite. An anion that has 1 more oxygen atom than the ATE is given the prefix per, as in short for hyper. So perchlorate. And here's a list of common polyatomic ions, and you're definitely going to want to refer to this as you get ready to move into the quick write and the quiz for this combined section. So, naming compounds with polyatomic ions. Follow these simple steps, right? Writing out the ions with their charges side by side, cation first, and then crossing over the charges, right? Crossing over the charges, be A-OK. But please remember, elements in polyatomic ions are bound together in a group and they carry a characteristic charge. So, for example, the sulfate polyatomic ion always has a -2 charge. The ammonium polyatomic ions always have a +1 charge. Also, the formula for a compound with polyatomic ions shows how the atoms in each ion are in fact bonded together. For example, KNO3, potassium nitrate, right? We are bonding the potassium to the nitrate as a whole. And so we are not bonding the potassium to the nitrogen, for example, and leaving the oxygens left over. Oh, no. We have to bond them all together as units. The hardest part about naming an ionic compound that uses a polyatomic ion is simply knowing the name of the polyatomic ion. Once you have that, your traditional binary naming systems work perfectly well. So let's look at a few examples. Here we have a phosphate. Okay, this is going to be one of the ones that's very, very helpful, beneficial for you to memorize. Now, phosphate has a -3 charge, and that's always known. Phosphate always forms a -3 charge. We're bonded to 1 iron. So we know that the iron must balance out that -3 charge with a +3 charge. So this becomes iron 3 phosphate. Remember, we have to have that Roman numeral because iron can form multiple charges. We don't know if it's the iron 2 variety or the iron 3 variety, so we have to communicate that. We have the sulfate anion, polyatomic ion. It always forms a -2. Sulfate is always a -2. It's bonded to 1 calcium, and so that calcium is balancing out that charge with the +2 charge. Now, when I go to name this, however, I don't have to say calcium 2 sulfate because calcium is a main group 2 element and therefore always forms the exact same charge, right? It always forms a +2, and if it always forms a +2, I don't have to say calcium 2 sulfate, I can just say calcium sulfate. Nitrate is another very common polyatomic ion that you want to be very familiar with. It always forms a -1. and silver always forms a -1. So we have the algebraic sum of our charges being 0. I don't have to say silver 1 nitrate because silver always forms a +1. So silver nitrate, and I'm done. And something very, very similar with potassium carbonate here. Here's my carbonate, right? CO3. Carbonate always has a -2 charge, but it's bonded to potassium. Now, these charges are always going to be the same. They don't vary. Carbonate is always a -2. Potassium is always a +1. But I have to balance out the negative charge with the positive charge. I can't change the charge on potassium to do that, so I change the number of potassiums I have, so I have to have 2 of them. But again, potassium always forms the same charge. That is not going to vary, so I do not have to communicate what the charge of that potassium is, so the name is simply potassium carbonate. So let's move on to another sample problem. Write the formula for 10,4-sulfate. So first we're going to write the symbols for the ions side by side, writing the cation first, right? That's the first thing that we always have to do. Write them side by side with the cation first. Then cross over the charges to get your subscripts. And then add parentheses around the polyatomic ion if necessary. And in this case, yes, it is necessary. The total positive charge is +8, and the total negative charge is -8. The largest common factor of the subscripts is 2, so the smallest whole number ratio of ions in this compound is 1 to 2. And that's going to make the correct formula SN parentheses SO4 2, right? 2 sulfates for that 1 tin. Unlike ionic compounds, as we transition into molecular compounds, naming molecules, unlike ionic compounds, molecular compounds are composed of individually covalently bonded units, or molecules. As with ionic compounds, there is also a stock system for naming molecular compounds. We can do that very, very easily. The old system for naming molecular compounds is based on the use of prefixes, and that's the form that we are going to practice in this class. So we have CCl4. That's carbon tetrachloride, with tetra referring to 4. We have carbon monoxide, with the mono referring to 1 oxygen. Carbon dioxide with the di referring to 2, as in 2 oxygens. Here is a table with some common prefixes that you want to be very familiar with. Mono, di, tri, tetra, penta, hexa, hepta, octa, nona, and deca, and examples of each. As we start to focus on molecular bonding, remember that the word molecule is specifically reserved for items that are covalently bonded together. And you're only going to experience covalent bonding if you have 2 or more non-metals in contact. Now, the reason that we don't have to use prefixes when we talk about ionic bonding is because we assume that the algebraic sum of the charges is going to be 0. And since we know what the charges are in an ionic compound, because either we know what group it's in, therefore how many valence electrons it's going to have, we know that that's always going to be the same charge. Or if we have a transition metal that forms multiple charges, we have the presence of a Roman numeral that will indicate that charge for us. Either way, we know what charges to balance. But when we talk about covalent bonding, we are not talking about balancing charges. We have all non-metals bonding with all non-metals. There are no ions. All we're doing with covalent bonding, remember, is sharing electrons in order to complete an octet of valence electrons so that we can get that noble gas electron configuration, get that lower energy configuration, because nature favors lower energy configurations. So in order to communicate to the reader how many of each type of nonmetal is present, you have to say it very, very explicitly, and we use prefixes to do that. So for this first example, we have dinitrogen monoxide. We have 2 nitrogens, so dinitrogen. We have 1 oxide, monoxide. Nice and simple. Trilithium nitride. When we have this 1 single nitrogen surrounded by 3 lithium, we have to say trilithium. When we have carbon tetrachloride, 1, 2, 3, 4, we can't rely on charges to balance this. We have to tell you that there are 4 chlorides. When we have phosphorus pentachloride, 1 phosphorus, 5 fluorides, you might notice that there's no mono in front of the phosphorus. That's the only time we don't have to explicitly say how many atoms are present. If there is only one of that first atom, you can drop the mono. For example, you guys already know about carbon monoxide. It's only 1 carbon and 1 oxide, but you don't say monocarbon monoxide, just carbon monoxide. That's the only exception to the rule. Now, I'm hoping you've noticed a little bit of an interesting thing in here. This top box, this trilithium nitride, lithium here is a metal. Lithium is a metal. So I'm not actually needing to say mononitride. Why? Because I've told you that there are 3 lithiums. There are 3 lithiums. And if there are 3 lithiums, that's going to take 1 nitride in order to balance those charges, because these are ions. These are going to be ions. And so it is possible you can use the prefix system to name all types of molecules. However, it is not convention. No one does that. In practice, we only use the prefix system to talk about the names of molecules. So let's move on to the next sample problem. Give the name of As2O5 and then write the formula for oxygen difluoride. So first up, a molecule of a compound containing 2 arsenic atoms. So the first word is diarsenic, right? That's 2 arsenic atoms, so diarsenic. The 5 oxygen atoms are indicated by adding the prefix pent to the word oxide. So the complete name is diarsenic pentoxide. Oxygen is first in the name because it is less electronegative than fluorine. In fact, fluorine is the only element that is more electronegative than oxygen. Because there is no prefix, there must only be 1 oxygen atom. The prefix di in difluoride shows that there are 2 fluorine atoms in the molecule. So the formula is OF2. Some covalent compounds do not exist in individual molecules, and so this is a special type of covalent bonding. Instead, each atom is joined to all of its neighbors in a covalently bonded 3-dimensional network. Subscripts in a formula for a covalent-network compound indicate the smallest whole number ratios of atoms in that compound. Some common examples are silicon carbide, silicon dioxide, trisilicon tetranitride. And so these covalent network compounds are things like diamond or graphite. It's carbon covalently bonded to carbon, but is a huge 3-dimensional network, much in the same way that crystal lattice structures are huge 3-dimensional structures. But for covalent network compounds, it's all nonmetals, hence the covalent part of the network. We also have special ways of naming acids and their salts. An acid is a certain type of molecular compound. Most acids used in the laboratory are either binary acids or oxyacids. Binary acids, by definition, are acids that contain 2 elements, usually hydrogen and some halogen. An oxyacid is defined as an acid that contains hydrogen, oxygen, that's why it's oxyacid, and some third element, which is usually some nonmetal. In laboratory, the term acid usually refers to a solution of water of an acid compound, a solution in water of an acid compound, rather than the acid all by itself. For example, if I say hydrochloric acid, I'm really talking about a water solution of the molecular compound hydrogen chloride, right, HCl, in water. Many polyatomic ions are produced by the loss of hydrogen ions from oxyacids. For example, when we put sulfuric acid in water, it dissociates to give us sulfate. When we put nitric acid in water, it dissociates to give us nitrate. When phosphoric acid dissociates in water, it gives us the phosphate polyatomic ion. An ionic compound composed of a cation and the anion from an acid is usually referred to as a salt. For example, table salt, NaCl, contains the anion from hydrochloric acid, which is Cl, HCl. Calcium sulfate, CaCO4, is a salt containing the anion from sulfuric acid, right, the sulfate. And the bicarbonate ion comes from carbonic acid. A few slides back, we considered some of the prefixes that go along with names of polyatomic ions, and we focused on hypochlorite, chlorite, chlorate, and perchlorate. So let's take a look at what this actually looks like. So we have the hypochlorite ion. We know that this has 2 fewer oxygens than the same type of ion that has an 8 ending, right? So chlorate. Hypochlorite has 2 fewer oxygens. We already know that. But when we add that 1 acidic proton, right, it's only going to be 1 acidic proton because hypochlorite has a -1 charge. We call this hypochlorous acid. Moving up in oxygen, we have just the chlorite ion. This has 1 fewer oxygen than the 8 ion. Again, anything that has "ite" in the name, chlorite, we replace that with OUS when we're turning it into the name of an acid. So chlorite becomes chlorous acid, right? 1 more oxygen. So let's increase oxygen 1 more time. Chlorate, this is one of the most common ions that we see in the real world, but also in this course. And if you try your hand at AP Chemistry next year, we talk about chlorate quite a bit. That ATE is changed into IC when you're naming an acid using this ion. So chlorate becomes chloric acid. And then when we have even more oxygen, we have 1 more oxygen than the 8 ion, it becomes a perchlorate ion. You might wonder, isn't the the opposite of hypo, like we saw in hypochlorite, wouldn't the opposite be hyperchlorate? Well, yeah, we actually just say perchlorate for short. It's short for hyper. Perchlorate means it has 1 more oxygen than that 8 ion, and so when we create an acid out of this, meaning we have that acidic proton, that hydrogen on there, it becomes perchloric acid.